In this lecture, we will see some performance parameters of BJT. We are going to focus on how these are defined, what is their ideal value, and how their value can be improved. That's all you should know about these parameters. Let's start with emitter injection efficiency. Emitter injection efficiency is defined as current of injected carriers at emitter junction due to carriers of emitter divided by the total emitter current. In case of PNP transistor, we have emitter injection efficiency to be equal to whole diffusion current at emitter junction divided by total emitter current. The ideal value of emitter injection efficiency is 1, and to improve the value of emitter injection efficiency, doping concentration of emitter should be made as large as possible compared to doping concentration in base. As higher the doping concentration in emitter, higher will be the current of injected carriers by emitter. The second performance parameter is transport factor. Transport factor is defined as injected carrier current reaching collector junction divided by injected carrier current at emitter junction. Therefore, transport factor is equal to whole diffusion current reaching collector divided by whole diffusion current at emitter junction. Its ideal value is also 1, and to improve the value of transport factor, we have to keep the value of base width very small compared to diffusion length, as by doing so, more number of charge carriers coming out of emitter will diffuse to the collector. The third performance parameter is large signal current gain, which is also referred as current transfer ratio. This is a very important parameter. Current transfer ratio is defined as a ratio of collector current increment to the emitter current change from 0 to its operating value. This modulus function simply means that current transfer ratio is always positive. Not only this, all the performance parameters have positive values. So you can put the sign according to the reference direction of different current taken in the diagram of BJT. Like in the shown diagram, we have current transfer ratio to be equal to negative of collector current minus reverse saturation current divided by emitter current. You can also say current transfer ratio is equal to final current minus initial current divided by emitter current, where final current is the current in collector junction after BJT is formed, whereas initial current is the current in collector junction before BJT is formed, or in other words, it is the current flowing in isolated reverse biased PN junction. Initial current is actually reverse saturation current, and final current, which is the collector current in the BJT, is equal to reverse saturation current minus injected carrier current at collector junction. We have not considered generation current, but it does not matter because generation current will remain the same in both the cases, and while finding the difference, the generation current will cancel out. Solving the equation, you will get current transfer ratio to be equal to injected carrier current reaching collector junction divided by emitter current. By simple rearrangement, we can also write current transfer ratio is equal to transport factor multiplied by emitter injection efficiency. Current transfer ratio is very important, and this relation is also very important. Its ideal value is also equal to 1, as it is the multiplication of transport factor and emitter injection efficiency. If we have to improve its value, then the two conditions which we discussed, one for improving the emitter injection efficiency and the one we discussed for improving transport factor, need to be satisfied. One thing you should always remember that you are being taught here what is relevant to you. You should not think that you know everything about BJT. In higher studies, you may study more currents and may study few more performance parameters. Like we have collector multiplication ratio, but here we ignore it completely so that the subject is easily understandable for graduate level students. This ratio actually considers the phenomena of avalanche breakdown, but obviously it will become very complicated if we consider different phenomena all at once. We consider collector junction is free from avalanche breakdown so that the value of collector multiplication ratio is 1, which is its ideal value. You may not see this parameter in standard textbooks. However, there is one other parameter which is usually ignored but still you should know. This parameter is recombination factor. Recombination factor is defined as ideal forward bias current of ammeter junction divided by forward bias current considering recombination current. The recombination factor is less important as generally the value of recombination factor is very close to 1, and in numericals we generally take its ideal value 1. The combination factor becomes significant when the forward bias voltage is lesser than cut-in voltage. However, in real-life applications, the forward bias voltage is greater than cut-in voltage, and most of the times, the recombination factor is simply ignored. These are the 4 performance parameters that you should know about.